Hello everyone, or almost everyone. I hope you're all still wide awake after this heavy lunch. That's why I left the lights on, so you have some hope to keep you awake. So as you can see, the name of this talk is Clef Design, Thoughts on the Formalization of Program Construction. And my name is Klaas van Schelven. I've spent most of my adult life as a software developer. So either as a contractor of some sort or in a more entrepreneurial setting, so setting up my own company. And the last such venture was actually a company that I got out of in late 2016. So by that time I decided to take a sabbatical, and the main project that I did in that sabbatical has been something called Expressions of Change. So the paper I'm presenting today is about that project. Okay. So what is this talk going to be? First I'm going to talk a little bit about the project's motivation, and then I'll dive into the specifics, and this is the part you'll probably all be clamoring to see and to hear about. And then the most exciting part, of course, is always the demo. So let's hope it goes well. Or for you, maybe let's hope it doesn't go well for more entertainment, we'll see. In any case, if you have questions of the kind of nature where you want something clarified, if you're completely confused about what I'm talking about, don't hesitate to ask. Of course, if you have more philosophical questions, do hesitate to ask, and don't ask, because it will mess up my timing. So, as promised, some words about the motivation first. So first, software evolves, right? We all know this. Successful software will be go into maintenance mode. Another slogan is like software is either dead or changing. This commonly cited figure is that 40 to 80% of software development cost is in maintenance, so take that for what it's worth. But in any case, we know that software changes, and the basic building block of software is something like this. So this is my rendition of a text file. Of course, we've moved slightly away from this punch card in our day-to-day lives as developers, but not too far. And one of my main points is that these text files, that they have no concept of history. So in your conversation with your compiler or interpreter or other parts of your tool chain, you just present this thing to your compiler, but you don't tell the compiler that there's some relationship with this other very similar thing that you just presented it only moments before. So it's not really a conversation you're having with your compiler, or you're having a conversation with some kind of dementia patient. So you ask, of course, what about Git? We've solved this problem, we've acknowledged that this is a problem, but now we have some version control Git or some other system. So now, then I show this. I hope this is clear, but this is my favorite metaphor for version control. So as you can see, there's a fire escape built on the outside of a building here. And this is what you get when you have changing requirements after the fact. So first you build a building, and then someone comes along and says, wait, this is not safe. We have some fire safety regulations. You need to fix this. And then you say, okay, no problem. I'll just put this fire escape on the outside, problem solved. But if you knew this requirement beforehand, you wouldn't come up with this solution. So I say modern buildings don't have such fire escapes. They just have integrated them into their building. And I say modern programming environments should have integrated support for program modification. So program modification is a key part of our problem domain, and let's make sure that this is somehow reflected on the solution side. So what is the general direction of the solution then? The slogan there is change as a primitive. So instead of using text files as our main building blocks of software development, yet let's take the modifications themselves and somehow reify them and make those the basic building blocks of software development. And we do that by making it both the way that people communicate to each other about programs in terms of program modification, and make it into the shared interface across the programming tool chain. So that's a great goal, to reify program modification, but the next question is, of course, what does it even mean, right? We need some kind of formalization. We need to choose a formalization for this program modification. And given that there are many possible formalizations, we also need some kind of way of ranking them. So we need some framework to decide on what is a good formalization. And this choosing of a formalization of program construction is, as you could have deducted from the subtitle of the talk, is the main subject of this talk. So another way to think about this is that in computer science research, there's a lot of thinking going on about formalizations of program structures, but not very much about construction, so let's do that for now. By the way, I do kind of interchangeably use modification and construction, right? Modification is simply constructing from not scratch. So we choose formalization, and then we just record everything in terms of that formalization, and then we reap the benefits automatically, right? So that's this slide, which is the South Park GNOME. So profit will come automatically. Of course, profit doesn't come automatically. So I have some ideas on where to look for the gold, so to say, where to look for the profit. So before diving into the design of this formalization, let's very briefly talk about where the gold could be. So it could be in at least 2 locations. So first of all, the change-aware tools. So you can just take any old programming language and then make all the tooling change-aware. So make all the tooling aware of the fact that there is structured historic information available now for your programming language. And an example could be static analysis. So I assume that you all know what static analysis is. So there's any kind of analysis you can do on your program without actually running it. And now if you have structured information available about the program's history, you can do that. Well, the naive thing is you can at least do that for any point in time of your program. So the static analysis, you're usually not doing it for no reason at all. You're usually doing it for some reason. So to discover something about an error or to get some information about something that could possibly be wrong about your program. And the static analysis will tell you usually where something could be wrong or is wrong in your program. And now if you do this all over time, then it will also tell you when you broke your program or when you created some condition that is somehow interesting for you. And that's great because that's another important piece of information that will help you to actually solve this. Of course, the naive approach is super inefficient. You just multiply the computational effort by the amount of modifications that you do. So there is actually some ways to do it slightly less naively. I'm not going to talk about those today, but I'm just going to claim that I've found them. And I'm just going to click with this thing. And the more ambitious goals are along the lines of historic metaprogramming. So if metaprogramming is all the kinds of things where your program knows stuff about itself, can do that in a historic sense as well. So the assumed benefits would be things like better support for data migration and, for example, not having to reboot your program every time you make a change. Okay, this is now dead. So enough about this motivation. Let's actually dive into the meat of the talk. Let's talk about the design of a formalization of program construction. So first we have to talk about the design space because we're talking about the formalization of program construction, but the question is program construction of what kind of programs, right? What is the structure that is being constructed? And then we're going to talk about the design goals. So that's the thing I already hinted at. There's going to be a whole bunch of possible formalizations. We have to pick one, so we need a framework where we can think about what are good formalizations and what are bad ones. And finally, I'll show an actual particular design. So this is where you all start cheering. I actually did a similar talk like this at the Haskell meetup, and surprisingly, someone actually started cheering there, which I thought was funny, given that it was a Haskell meetup. Anyway, the structure under consideration are S expressions. So now, let's go very quickly through the definition, given the fact that we're here at the European Lisp Symposium. So an S expression is either an atom, and here I'll just say an atom is anything, I'll pick symbols and numbers. Of course, there are as many definitions of S expressions as there are Lisps, or almost as many. So here the thing of importance is that we can print it on screen, and other than that, it just generalizes for our purposes. And second, it's a list of S expressions and then we typically print those using parentheses. So here we have one, so this is a list expression, and it consists of 3 further expressions. So this is in plus atom, a further list expression, and the atom 12. Let me just try to, so sad. Okay. So, why would we pick S expressions for this purpose? Well, first, there's a minimal definition of the S expression, so it fits on a slide, and that's useful for a bunch of other reasons. So it lowers the communication overhead, it lowers your own mental overhead, it's easier to implement, and finally, it makes it possible to come up with a concise formalization of program construction. So if your structure definition is already taking up half a book, then reasoning about how to modify such structures in a structured way is going to take up probably even more than half a book. So that's an important bunch of reasons to pick S expressions. And further, S expressions have a structure that is explicitly visible. So you can look at an S expression on screen, and you can you're pretty much looking straight at the AST there. And I think that is probably, it might not be a requirement, but it makes it a whole lot easier to actually directly manipulate S expressions, or the structure under consideration, which is what we want. We want to manipulate in some structured form. If you have a structure that looks very different on screen than the underlying representation, then it's very hard to manipulate the underlying representation in a way that's understandable for the programmer. And finally, of course, there's a whole family of languages available that you can then build on top of this, and given the fact that it's all about programming language design, it's useful. So let's build up a couple of intuitions first to think about what is a formalization of program construction, what's the kind of thing we want to build, and then get slightly more formal later. So first, let's tell you a little story of program construction in plain English. And of course, such a story will ultimately not be useful for our purposes because, well, in the end, we want to build something that we want to end up with something that the tools can actually use to talk to each other, and they don't talk English usually. But it's still useful to imagine what we want. So here it is. So we can start with this expression, and we remove the atom plus. That leads to this other S expression. We insert hello, and gives us another one. So the details are absolutely not important. What's important is to have this feeling of adding and removing stuff, maybe shifting stuff around. So the next question is, what would a typical vocabulary or typical formalization of program construction look like? So, well, I've already talked about adding and removing. So what we can see is that there's at least a couple of kinds of operations that you can do. And then typically those kinds of operations will actually have different properties each. So if you delete something, you might only have to specify where to delete it as part of a list. But if you add something, you actually have to somehow specify what is going to be added. And there's going to be some relationship with the structure. So if you have a structure which has, like S expressions, different subkinds, so you have atoms and lists, then there's probably going to be things to modify both the atoms and the lists. Okay. So the typical design decisions are then to actually pick a set, like out of all the possible kinds that you can come up with, pick a couple of them, and then choose out of all the possible properties that you can come up with to specify the further information, choose those. So finally, some terminology, because that's always the favorite part of everyone's when they're listening to a talk. But we are kind of forced to talk a little bit about terminology because for program structure, there's of course well-established terminologies because, well, we've been studying the subject for a long time, so we have so we talk about grammars and parsers and terms and whatnot. Well, as far as I know, no one's thinking too much about formalizing program construction in a very structured way. So there's no words, so then we have to talk about a vocabulary of program construction all the time, and that gets tiresome. So I've picked a random almost random metaphor. So it's a musical notation metaphor. It will carry you as far as any metaphor will carry you. Any metaphor breaks down at some point. I think it's useless regardless. So the first word there is clef, which is also reflected in the title of the talk. So that's basically what I've used to designate a formalization of program construction. So, well, just diving into the musical notation very briefly. So a clef in musical notation is one of these symbols on the right. Why would you use the word clef to pick this formalization of program construction? Well, here's a bunch of notes on some musical score, but what are they? We don't know what they are. We need something to give semantics to this bunch of notes. So we put this clef in front, and now the people of you that know music will know that this is the meaning of these notes. So, well, of course, I've already used notes. So that's the word I use both to designate a kind of modification and a particular modification. So you have, for example, adding stuff would be a note, and then also to add the third to add as the third element to a list such and such thing. So both the class and the instances I use the same word. And score is just a sequence of notes that can play one after the other. I've kind of snuck the word play in there as well. So playing is applying one of these notes, so applying a modification on a given structure, which then yields a new structure, and a score is to do that in sequence. Okay. More notation. So you can use S expressions, luckily, to actually kind of write down these notes. So here's a note, and then which note it is, we'll use the first element, and the rest of the attributes go in the rest of that list. And if we put a bunch of these notes in a list, then we call that a score. By the way, actually, this taking of S expressions as a notational device, that's not in any way required, but it's, of course, it's useful. One of the uses that you have is that you can then apply this whole idea of program construction on the mechanism of construction. So you kind of get, well, you have the ability to rewrite history using the same tooling as you had when you write the original program. Okay, so let's discuss a couple of goals for a clef. Now we can say clef instead of formalization of program construction. So remember, there's many possible clefs for any program structure. So if you have a given program structure, you can, in fact, there's infinite ways. You can always trivially add, like take a given one of the infinite programs that are possible to write in that structure, and then say there's a special note in the clef to add that particular structure. So in any case, we need some mechanism to choose between them. And first of all, I'd say that it's useful if the clef is actually complete, so that you can go from any given program that you have and you want to modify it into the program that you want to have, such that that is possible. So that means in practice that it should at least be possible to go from any given list expression, for our case, from any given list expression to any other list expression. Okay. So second goal would be a brevity goal. So if you have a clef which has 100 special kinds of notes, then which is not very little, I'd say, then the programmers that are expressing themselves in those notes need to know those 100 goals, need to know those 100 different notes, and your implementation across your programming toolchain needs to support all of them. So neither of those are good. And second, it says brevity twice here. So the second reason, the second way I think it's useful to have a clef that's able to be, well, the second thing that's useful is to have a clef that allows you to express concisely the typical modifications that you would do. And there, the advantage is mostly that programmers need to actually, or will usually read such kind of histories. If the histories are very far removed from what actually happened or what the programmer would expect to happen, then it's much more of a mental burden. And finally, there's composition. So now we have this awesome quote. So this is Hal Abelson. He has some wise words for you. When you think about the language, you think about it in terms of what are the primitives, what are the means of combination. So the question is, what does it mean for us, right? We've seen the concept of program construction, and now we want to think about means of combination in this program construction. But we are we might also want to do that in the context of program structure. We're still dealing with actual computer programs here. So, can you guys read this? Well, in any case, there's a table here, and I've tried to express that you want to look at the ways these two things themselves can be combined. So, let's see, horizontally, you can either completely ignore the composition of the construction, so you ignore the composition over time, or you can acknowledge, or you can have some mechanism of composition over time, and then here vertically in the rows, you can do both ignore or not ignore the same thing for program structure. So what does it mean? Well, first of all, if you ignore everything, that's not very interesting, so the first cell is empty, and the next cell is the situation where you have some mechanism of composition in the program construction. So you can organize somehow, the program construction is not just a single sequence of things, you can somehow compose those things. And then diagonally the other thing is where you acknowledge the composition of so you ignore the composition of construction and you acknowledge the composition of structure. So you acknowledge that a program typically has some structure. So a program may have modules, classes, methods, expressions, statements, or some subset of those means of organization or other means of organization. And the question we can ask is history available at any of those levels? So can we say what's the history of this module as easily as we can say what's the history of this particular expression? And of course there's also the situation where we acknowledge both. So much for the goals. Let's move on to an actual Clef. And again, I'm asking, can you guys read this? Okay. See happy faces. So, that's okay, but I cannot do it. So someone in the back would have to press one of the, yes, one of the gray buttons. That's the wrong one. Okay. Okay. Now you can definitely read it. I won't kind of linger over each of them forever. Just say that this has become atom. So out of nothing, you can create an atom. You can also set atom, which is given a particular atom, change it into this other atom. And there's become list. Out of nothing, there becomes a new list expression. Insert at a particular index a particular score. So that's a mechanism to insert into a list something new. And the relevant point here is that the thing to be inserted is itself expressed in terms of a score. So that's a historical story about what's to be inserted. You don't just pass it a thing to insert it, you pass it a mechanism of construction. And deleted index is just delete the thing at a particular index. And extend is very similar to insert, but there's a difference, which is that it changes the thing that's already there. So, well, that's basically it. So, and for your score to be played, it also means that it doesn't start with nothing, it starts with the thing that was already there. And then there's a chord, which is to play a number of notes, and so it's basically just a means of composition given, so it turns a number of notes into a single note. Okay, so now let's scare you by doing something quick. Okay, so that was not actually to scare you, that was to illustrate what's about to happen. So what's about to happen here on the left, can you guys see this as well? Okay. So here on the left there is a score. Well, actually I've left out this, to save space, I've left out the opening and closing parentheses. So now it's just a bunch of notes. But this is to be interpreted as a recipe for construction. And then on the right, so we'll play this, we'll go through this, and then what we'll see on the right is the thing actually being constructed. So the first thing is become list. So what we see now is that a new list appears out of nothing. And then we insert at position 0. So, well, we don't know yet what to insert, so we reserve some space on the stack or whatever wherever you want to reserve it, and we are going to start to play another score, which starts again with become list. Well, by now we know what that is, and then we insert a 0, become atom star. So there I'm cheating because actually there should be another thing on the stack, but because it's just one note, I'm assuming that you can follow along. And then same thing for atom 6, and then when we are done playing that score, push it back up. Okay, so by now you're getting the gist. So insert 2 more atoms, and then we extend. Well, this is exactly what I promised it would be. So we start with what was already there. So we extend the thing at position 1. Well, we put on our stack the thing that's already there, insert a new atom at the end, and then push that back. So much for an example usage of this particular clef. So the question is, did we achieve something that we wanted? Oh, and then I have to actually press down. So completeness is left as an exercise to the reader, or actually in the paper it's not left as an exercise to the reader, so it's left as an exercise to people who want to read, it's more precisely. But I can assure you, using these notes, you can construct any kind of expressions, super trivial. And so brevity, well, this is a harder point for me to make very hard and hard remarks about, because there's nothing to compare it to. But I think that with 7 notes, at least it conforms to it. It fits on the slide principle. So at least in that sense, I think it's easy enough to kind of communicate to people what the clef is. Well, that's as much as I want to say about it. Regarding the ability to succinctly express typical modifications, well, I've built an editor that implements this particular clef, and well, that seems to work pretty well. And some more evidence that this is actually useful to express typical modifications is the fact that acronyms like CRUD express something very similar. So we have create, update, and delete. Of course, we have an R in there as well. That's for reading and it's not relevant to modification. So, and actually on yesterday's talk, we heard about the edit buffer protocol, or actually that was a reference to a 2016 talk, but in any case, that had the exact same operation. So there is some basicness there that I'm just reusing, basically. The biggest open question is, like, should moving, for example, be an explicit note in the clef? So, and for composition, we return to this beautiful table. So first we look at this interclef question. So say we have the same, or at least, yeah, actually it is this, well, in any case, say we have this particular score. And now we say, okay, these 2 things at the beginning, these 2 first notes, they're actually related. So I'd like to organize them to reflect that. Well, that's actually what this slide is about. So yes, that's possible. You just put them in a chord, and now you have one note that expresses those 2 things together. So you can arbitrarily, hierarchically organize your histories. And then I'm just going to skip this history at any level because it's directly implied by this 3rd thing. So is there a meaningful relationship between the clef and the structure's means of composition? To answer that question, we have to remind ourselves what the means of composition are, both for structures and for clefs. So for structures, we all know it because we're Lispers. So structures are list expressions, and the main means, sorry, I should say that more precisely. Structures are S expressions, and the main means of composition in S expressions is the list expression, which is what we saw here. So we see this list expression, which consists of other expressions. So what about this clef? Well, here we have a score, and that composes a bunch of notes. So then the question becomes, what's the relationship? And well, here the answer is pretty obvious. So on the left, and that's kind of the starting point of the whole demonstration, of the whole example, is that on the left we play this whole score, and what it yields is the structure on the right. And inversely, if we ask this thing on the right, if we assume that this thing has some kind of historical memory, and that assumption is the implicit assumption in this whole venture anyway, because The whole point is that you're not just constructing things, the whole point is that you're constructing things and then will be able to ask those things later, meaningful questions about their history. So if we ask that thing, what is your history, we'll get this answer. So then the question becomes, given that that's the whole list expression, the list expression is composed of other things, can we also ask one of the things that it is composed of what its history is? And the answer is yes. So first I'll just show the answer. So here the answer is that particular become atom. And here is also a very brief history. But the more interesting case is the sub-expression. So we can ask the sub-expression, what is your history? And we can kind of extract it from the history of the whole thing by taking all the operations that were done on that particular S expression and concatenating them together. You'll get this. And by the way, so the key thing that actually makes this possible is the fact that this insert and extend operation are expressed in historical terms. So you don't just insert a thing, you insert a recipe for construction.